Alright, welcome to our second session for PCA visualization. We're going to go over a few things about indexing before we look at some more visualization. And I am going to talk about logical indexing. So let's create a vector called vec1 and make it the numbers 1 through 10. That's what I did here. So vec1 assignment and 1:10. Alright, and then let's do vec1 greater than 3. What does that give us? What it gives us is a logical vector in return where each element has false or true, true or false, telling you if that element met the condition. So we asked vec1 greater than 3. So it checks each element against this relation, greater than 3, and then lets you know if it was true or false. So 1, 2, and 3, which is what vec1 was, right? 1, 2, and 3 were all false because none of them are greater than 3. But 4 through 10 were all true because they are all greater than 3. And the same thing happens if you ask less than 3, right? So 1 is less than 3. 2 is less than 3, 3 is not less than 3, and the rest are obviously not less than 3. And then you can also do, is it equivalent to 3? Right? False, false, true. And you can also do, let's add here vec1, whoops, not equivalent to 3. And obviously everything but the 3 is going to be true, because the only one that is actually 3 is 3. Alright, and then you can also index using a logical vector. And so if you say, show me all the elements in 3 that are greater than 3, and you use this as your indexing vector, and you place it inside the brackets, it will give you all elements where that is true. So the indexing vector using the relational operator will give you return only those indices where it is true right here. So that's another way you can index. Okay, another great function is called duplicated, and it will take either a vector or a data frame or matrix, and it will tell you, it will return a logical vector if it's a vector, and it will return a logical vector if it is a matrix. If it's a vector, it'll tell you whether each one has a prior duplicate. So the first one can't have a prior duplicate, so it's going to be false. The second one does have a prior duplicate, right? Because the vector here is 1, 1, 1, 2, 3, 4, 1, 2. And so the second one is a duplicate of the first one. The third one is a duplicate of the first one. But then it goes 1, 1, 1, 2. That's the first time a 2 came up. Then it goes 3, and then 4, right? And then we do 1 again, and so this one is a duplicate of this one. And then we do 2 again, which is a duplicate of that one. So it gives, each one tells you whether it is a duplicate of an earlier value in the vector. So we create a new vector, run it again, tells us if it's a duplicate or not. And you can also, because it returns a logical vector, you can then index using that logical vector, and it will return all cases where it is true. So what is this going to return? If we subset or index vec2 by the result of duplicated vec2, it's going to return the numbers that have been duplicated, right? So it lets you know that these two were duplicated. But what we really want most of the time are the numbers that aren't duplicated. We want the originals, all the originals. And so what you do is you put this not logical operator, right? Relational operator, not duplicated. So we want the ones that are not duplicated in this vector. Okay, so what does the not duplicated look like? I'm just going to highlight that one part, right? And this is not duplicated, not duplicated. That is not. Okay, good. So let's return only those elements that are not duplicates. And there you go, 1, 2, 3, 4, 5. Alright, so now I'm going to show you briefly a way you can combine rows or columns, so vectors I should say. I'm going to show you how you can combine vectors and make them into matrices and even data frames. So let's go ahead and copy vec2 and call it vec3. So now vec2 and vec3 are the same. And then we're going to use a function called cbind. Okay? And what cbind does is cbind binds two vectors into a single matrix, making the vectors columns. Okay? So, and cbind only works with two vectors at a time. The first argument or the second argument could actually be matrices as well, but they have to be the same number. If it's a cbind, this would have to be a matrix that has the same number of rows as this is long, right? Because this is flipping this vector, making it tall, and it's going to just put it to the left of this vector, or if it's a matrix, to that matrix. Okay, so let's just see what it looks like. Cbind vec2 and vec3, and I called it mat1, and mat1 is indeed now a matrix, right? Just like that. And you can also row bend, or rbend, excuse me, which just stacks these on top of each other. It'll stack vec2 on top of vec3 and make it a matrix. Okay, so that looks like that, just like that. Alrighty. And here's another way of making another matrix. Okay, and notice what I did here. I took the matrix mat2 and I then stacked it on top of the vector 1 through 7. See? But notice this had the same number of columns as this is long, because you're stacking them, so they have to be the same width. Alright, but you can also just go ahead and use the function called data.frame, which does as you may think it does. Let's go ahead and just look. Okay, data.frame creates data frames, right? And this actually takes as many arguments as you'll give it, as long as they're compatible. So you could put a matrix, a vector, another matrix, another vector, and it squashes them all together. And the thing that's cool about a data frame is, so in a matrix, notice these are all numbers. All the elements are numbers, and they have to be the same class. So if you tried to put something in here that was a character, it would transform everything into a character, because that's the most common form that they could all have. You can't turn a C into a number, but you can turn a number into a letter, or not, excuse me, not a letter, into a character, right? The character of the number. Alright, so here we're going to go ahead and take mat1, and then we're going to call, and then we're going to, and one thing you should know is, data frame will turn all of these into columns. So this is going to be a column in the data frame. Okay, and in a data frame you can name the columns. So I'm naming this one new vec, and it will be these numbers. Okay, so let's see what that looks like. And I'm calling it df1, and there you have it. Okay, and so there's the name of each column, vec2, vec3, and then new vec. All right, and if you run duplicated on a data frame or a matrix, it returns whether the row, each row is a duplicate or not. So the first row is not a duplicate of a prior one. The second row is not a duplicate of a prior one, but the third row is. Now why is that? Well, if you look, it is all ones. Now just so you know, this right here is just the row numbers, okay? So that's just letting you know where you are. So row 3 is all ones, and row 1 is all ones. And so row 3 is a duplicate of another row, a prior row. As is row 7. It is 2's, which row 2 was. Okay, so we really care about which ones are originals or not duplicated. So you use the not logical operator, right? So not duplicated. And it will say the first one's original, the second one's original, the third one's not, the fourth one is original, the fifth one's original, the sixth one's original, the seventh one is not. There you go. And you can index a matrix or data frame using the logical indexing as well. So let's go ahead and try it. So df1 bracket duplicated parentheses, df1, close parentheses, close bracket. What happens? Oh, all right. So you have to make sure that you use the comma, because remember, you index a data frame or a matrix with, it has 2 dimensions, rows and columns. So that was just a little gotcha that sometimes, sometimes can get you. All right, so what's it going to return? Well, if you use duplicated, it will return the rows that have duplicates, but we don't care about that. We care about the ones that aren't. So we'll use the not symbol in front, and it returns only the original rows of that data frame. Pretty cool. So then you can name a new data frame, df2, using only the original rows of df1. So df2, assignment, df1, square bracket, exclamation mark, which is the not operator, or the and then duplicated, and then parentheses, df1, close parentheses, comma, bracket. Right? So df2. What does df2 look like? There you go. Only the original variables. All the duplicates are removed. Okay, so now we're going to switch over and do a little bit more visualization in principal component analysis, and I'm going to explain something I didn't explain, I don't think, clearly in class. I focused a lot on the loadings, right? So those are the eigenvectors. The thing is, that is not going to be the data, because when we transform the original variables, we perform principal component analysis on the covariance matrix or on the correlation matrix, not on the original data, right? So those are derived from the original data, but we perform the analysis on the covariance or correlation matrix. So to then transform the original data into the new transformed space, right? The space that now has each axis, each component is orthogonal to the prior. You need to transform the original variables using the loadings. Luckily for us, printcomp does it for us, and the way to get those is scores equal true. The scores are essentially when you take the linear combination of the original variables, right? So you're adding weighted, you're weighting the original variables and then adding them together, and that will give you then a score. Okay, and that score is now that observation's value in this new space. Okay, so it is now that in component 1, the new variable, it now has that observation has this value, right, in this new space. Okay, so just think of it as component 1's value for that variable. Okay, so the scores are the new variables, the transformed variables that are these sort of latent variables, right? So component 1 will be the latent variable something, and in class we talked about what those could mean. All right, so printcomp, your data, we're using the iris data, so just type in data, parentheses, iris, close parentheses, and that loads the data for us. And then I called it iris.pca assignment printcomp parentheses iris, and then we're just going to run it on the first 4 columns, because the 5th one is the species thing and it's a character or a categorical variable. Okay, so make sure you have that comma in there. And then the argument is scores equals true, because we want it to return the scores, right? And if you look in printcomp, that's what it says. It says here, scores, a logical value indicating whether the score on each principal component should be calculated. And we want it to do that for us. And we're going to use core equals true here. That may or may not be appropriate. I don't know exactly what scale it uses to measure these the sepals and the petals. And maybe this is not the right thing to do, but in this case we're just going to do it. And we'd do a little more research if we actually cared. All right, so let's create it. Great. Now, load the library, the lattice library, because we're going to use those functions in there to get a better look at our new variables. All right, and we're going to use the data frame function. All right, so we're going to I call it iris.pca.data, and we're going to create a new data frame, right, in the assignment variable, then data frame, and then grab the scores, right, which you do using the $sign. So iris.pca $scores, comma, and then we're going to grab in the original variable iris $species. So we're grabbing the original species variable because it's a categorical variable, and we want it each observation, right, in the original data set. The scores, each row corresponds to the same row in the original variables, but now the row in the principal components are in that new projected space. And so the species still corresponds there. So what we're doing, this is taking the scores, right, and then it's going to slap the species on the right side of it, okay, and create it. And we can, just to get a look at it, we can do summary iris.pca.data and see what that looks like. Whoops, I hit Command Enter. Here, I'll go ahead and actually do that. So summary iris.pca.data. Okay, so as expected, these are scaled, so the mean is 0. Okay, and they have different, minimum, maximum, because they are scaled. But notice how it names the species variable. Because when we called it here, we didn't name it. It called it iris.species. What R does is it automatically replaces illegal characters with a dot, right? And so the $sign, you can't have a name with a $sign in it, and so it replaces it with a dot. So we'll just go ahead and keep that. You could name it here just to keep it consistent, and the new variables are called component 1, component 2, component 3, component 4. All right, and we could also see the names, and that's where we see that as well. Okay. All right, so let's go ahead and use some plots here in the lattice library or package. We're going to use the box and whisker plot, and remember the format. Go ahead and look up, BW plot, and it uses that formula interface, if you recall. And so we want to look at the species across component 2, and it's gonna, so this here says plot species against component 2, and you're gonna get those things from the iris.pca.data. Right, so data equals iris.pca.data. Right, so BW plot iris species. Here we go. Let's see what happens. All right, so we see that in component 2, the values of setosa are from -1 to about 0.5. But notice versicolor, I'll just call it, is a bit further to the right. So whatever component 2, whatever the latent variable in component 2 is, versicolor seems to be quite a bit different from the other two. Okay? So that's something we can get from that. Alright, so let's look at an XY plot, and let's plot component 1 against component 2 dependent on the species. Alright? And we'll call that from the iris.pca.data. Alright, let's just see what we can see there. Alright, well, we notice that it seems like there is, look at this, it's kind of, this is pretty flat, right? There's really nothing going on. Component 1 and component 2 don't really have a relationship, which is good, right? That's what we expect. Seems to be a little bit more of a relationship here. Maybe, but not really strong. Okay, so, and that's to be expected. They're components here. So yeah, you see that component 1 and component 2 seem to be pretty independent. There's not a lot of the same information that's covered by them. That doesn't have to be the case, right? They're orthogonal, but they could cover, they could explain some of the variance that's explained by the same latent variable. Okay, so it doesn't have to be this way. But so then that raises the question: Did the PCA actually split the original variables into new orthonormal variables? Right, because that's what it's supposed to do. So let's load the psych library, and then psych inside the parentheses, and we'll run pairs.panels on iris.pca.data. And let's see what happens. Whoa, what the heck? Why are these all 0? I mean, what's going on here? Right? And then why are these so big? What 0.94? Well, it did what it was supposed to do. Component 1 is completely orthogonal to component 2. They are not correlated, right? And they're not correlated to any of them. Like, none of them are correlated. So PCA worked. Looks kind of magical. I mean, look at this scatter plot, right? It is completely normally distributed, right? Here you can see it's sort of bimodal, which means this could be versicolor. I'm not sure, but it looks like something funny is going on here, right? So they are correlated with the species, which makes sense, right? We didn't. If these components describe something that is relevant to the species, they will be correlated. We didn't include species in the PCA because this is the variable that we're interested in trying to predict. So look, these look pretty normally distributed, right? So this is the normal part, normal. These are normal, and it also they look IID, right? So these are orthogonal and normally distributed. So it looks like PCA worked. Pretty cool. All right, well, I hope this has been useful, and if you have any questions, please ask.